Hello everyone, welcome to MindSpan Education. In this video, we will develop the notion of independence of random variable. We are already familiar with the notion of independence of two events. Let's say if we have two events, that is A and B, then by definition these two events are independent if the probability of happening these two events is equal to their product of individual probability. And we have also seen the intuitive definition of these two random variables being independent. That is, let's say under this event B, if I have to find the probability of this event A, then that will be equal to the probability of event A. So intuitively, when you are told that B occurred, this doesn't change your belief about A. So this conditional probability of A is same as the unconditional probability. We have a similar definition of independence of random variable. Let's say this random variable X, and we have a event that is A. So the mathematical definition is that event A and the event that random variable takes on a specific value, that is little x. So the probability of these two events happening at the same time will be equal to the product of their individual probabilities. And this has to be true for all the values of this little x, for all x, right? And the intuitive definition for this case, so let's say we have given this event A, and if under this condition that we have given this evidence A or this event A has occurred, under this condition, if I have to find the probability that random variable x takes on a specific value, this probability will be same as the probability of this random variable that takes a specific value little x. So if I tell you that A occurred, this is not going to change the distribution of this random variable x, right? So let's say if I have to write this same in terms of the PMF notation, so we are talking about this random variable x under this given condition A, or this event A has occurred. So this is the conditional PMF, or the probability mass distribution function. If these two events are independent, then this unconditional PMF will be same as the this conditional PMF will be same as the unconditional PMF. So the conditional PMF of this random variable A under the condition A will be same as the unconditional probability PMF of this random variable. And we have also the symmetrical interpretation. So here we might also say that under the condition that random variable x takes on a specific value little x, if I have to find the probability of this event A, and let's say if these two events are independent, then this probability of this event A under the condition that random variable x takes on a specific value little x, that will be equal to the probability of this event A, right? And this has to be again true for all the values of little x. So if I tell you that the value of x, then the conditional probability of this event A is not going to change. It will be same as the unconditional probability. Okay, now we can move and we can talk about the independence of multiple random variable. Let's first of all talk about the independence of two random variable. Let's say for an experiment we have two random variables defined, x and y, and if these two random variables are independent, then by definition of independence, the probability that random variable x takes on a value little x and y takes on a value little y, happening of these two events simultaneously, the probability of that will be equal to the probability that random variable takes on value little x times the probability that random variable y takes on the value that is little y. So if we have two random variable for an experiment, and if these two random variables are independent, so by the mathematical definition of independence of two random variable, happening of these two event will be equal to the product of their individual probability. If I have to write the same thing in terms of the PMF notation, so we are talking about the probability, we are talking about the random variable x and y, and happening of these two events simultaneously, that will be equal to the product of their individual PMF. So the product of the marginal PMF of this random variable x times the product times the marginal PMF of this random variable y. So what I have done, I have just written this in terms of the PMF notation, that is all. And at this time you should be comfortable with these notations. So what is independence in terms of the multiple random variable? So, or if I have to tell you the intuitive definition of the independence of these two random variable, so when I tell you that the value of y, and no matter what value I tell you, your belief about x will not change. So the conditional PMF of x given y is going to be the same as the unconditional PMF of this unconditional PMF of x. And again it has to be true for any value of argument of this PMF. And here also I forgot to mention that this relation should be true for all possible values of x comma y, right? So you will, if these two random variables are independent, you will have to check for all possible values of x and y for this condition, and you found that for all possible values of x and y this relation is true, then you can say that these two random variables are independent. Or in terms of the intuitive definition, this conditional probability mass function of this random variable x given y will be equal to the unconditional probability mass function of this random variable x. And again this has to be true for all possible values of this argument, that whatever it takes. We can have the symmetrical interpretation also. So let's say we might also say that under the condition that this random variable x takes on a any value, no matter what value it takes, the probability of this random variable y, or the PMF, conditional PMF of this random variable y under the given condition x, that will be equal to the unconditional PMF of this random variable y. So what we have done, we have just interchanged the role of x and y. So it might happen, right? We might also give you that y has occurred. Under this condition, we might ask what's the probability of this x that random variable takes on a specific value, and if these two are independent, then it will be same as the PMF of this random variable x. We might also give you that this condition that random variable x takes on a specific value, and no matter what value it takes, and under this condition the PMF of the random variable y, and if these two random variables are independent, then no matter what the condition or what's the random variable x takes on value, this conditional PMF will be same as the unconditional PMF. So the point is that you might given this condition or this condition. Based on that, you will have to write this, right? Now we can proceed further and we can talk about multiple random variables. Just now we have talked for the two random variable. The idea will be same. So let's say if we have three random variable, that is x, y and z, and if these three random variables are independent, then the mathematical definition of this independence, random variable x takes on a little value little x, and random variable y takes value little y, and random variable z takes this value little z, happening of this event, the probability of this event happening at the same time, and if these random variables are independent, then this will be equal to the product of their individual probabilities. Again, if I have to write this in terms of the PMF notation, since we are talking about happening of these event simultaneously, the probability of that will be equal to the product of their individual probability marginal PMFs. So marginal PMF of y times the marginal PMF of this random variable z. Same, I have just written this as a PMF notation, and the very important point is that this has to be true for all possible values of x, y, z. Here the definition is for the three random variable, but we can imagine how the definition for any finite number of random variable will go. So the joint PMF of all the random variable can be expressed as the product of their corresponding marginal PMF. What's the intuitive interpretation for this case, or for this multiple random variable, and when these multiple random variables are independent? So it means that the information about some of the random variable will not change your belief the probabilities about the remaining random variables. Any conditional probability and any conditional PMF will be the same as unconditional one. We will see the example in next video. Thank you.